Hello, my name is Trent Greer, and this is my attack, reproduction, and presentation of a Linux kernel module rootkit and a command and control server. Rootkits are a form of malware that allows a malicious actor to gain unauthorized control of a computer system while concealing their activity. Rootkits often make up part of a larger attack, such as spyware or even a distributed cryptocurrency mining operation. This is why my specific implementation is used to conceal a command and control server which has unauthorized privileged access. Here is an overview of my rootkit and command and control server. The larger arrows represent the creation of the other processes. The smaller arrows represent connectivity between the processes. There is one thing missing from this diagram, which is the client, which sends commands to the server. There is an original executable which contains both the payload and rootkit of the malware. However, the target must choose to execute said program for one reason or another. The original executable has no way of executing on its own and would be relying on another route. This can include something like social engineering or disguising itself as a safe and reputable program. Once executed, a new command and control server is created, compiled, and executed, and a Linux kernel module rootkit is compiled and installed. The original executable then deletes all source files so as not to alert the user of what has occurred. In addition, the program passes the PID of the command and control server to the rootkit, where it is used to hide said PID from programs such as process status. The rootkit also hides all files starting with CMC, which is used to identify command and control files. They're hidden from user commands such as ls. This is achieved through hooking a syscall identified as present in both these commands and then inserting our own function in its place. We also gain root level access through this module. The command and control server sets up a socket and waits for connectivity. This is where a malicious actor can then send commands from a client and use user space commands and gain root level access. A malicious actor does this through using the previously hooked functions in the rootkit to take advantage of the kernel space. Most of this rootkit's functionality relies on hooked system calls. Function hooking is the act of making it so when a process calls a function, a different custom function is called instead. This allows attackers to disrupt detection tools as we have taken control of the functions these tools rely on. We can use them to directly utilize rootkit functionality as well. For example, one function this rootkit hooks is the kill system call. As you will see in the demo, using the kill command with the signal 50 will tell our rootkit to make us root. Deciding what function to hook depends on your intentions. The project specifications say a rootkit like ours needs to be not visible in the file system or process list, so we can look at what these call by using strace. strace tells us that these rely on getDense64 to get items from a directory. This is perfect for ls because ls does exactly that, and perfect for ps because ps works by reading files in the proc file system. Hooking a system call specifically is fairly straightforward. First, you must get the syscall table. If you are using a kernel version below 5.7.0, you can simply use k-all-sims lookup name. However, starting at kernel version 5.7.0, this function was purposely obfuscated for use to help prevent malware development. So instead, we must find it using kprobes. This was one of the technical challenges I faced when developing this rootkit. Then we find the syscall from the syscall table. Each syscall has a predefined slot in the table's array. So by looking at the reference, we can find the correct index for our syscall. Then we store the original syscall function somewhere so we can revert it back if need be, and point the table's index to our new function. So right now we're in our demo folder. The only thing in here is this malware executable. Obviously, in a real-world scenario, this would be named something different, or disguising itself as a trusted program, or be ran through some sort of social engineering. It would not be called malware. On the left here, it's just compiled from this malware.c file. All this is it has all the information from other files that are necessary to be ran with this attack. So it's just done in this kind of fprintf format, and then it's got some system calls on the bottom that compile these, remove unnecessary files, and then execute them. It also passes the PID of the command and control server to the rootkit in order to conceal the command and control server. This is all written using a script except for these system calls at the bottom. So it wasn't typed out by hand. If we run the malware just on its own, we get that it must be initialized with sudo or be in root. So we do, and it takes a little while to run, but not too long. And so once the malware executable is terminated, we should have our rootkit installed. You won't see anything. You won't see anything different. But if you do something like so CNC is the prefix we use for our command and control server. So it's supposed to hide CNC from commands like ls. So as we can see, the file is not showing up. But if we do, we can see the file still exists. You can also check for processes. Our command and control server is running, but if you do PS, it doesn't show up as running. So to the user, it looks like nothing has happened, and this is pretty good. And then we also hooked some system calls. So for example, we hooked the kill command, and right now we are in just regular user permissions, but we can become root by using our hooked system call kill. It's got a special signal 50. If we use a signal 50, it'll know to put us in root. So just type in any process number. It doesn't have to exist. It will actually call the real kill command, as to not hide that from the user. So no such process. But if we look at ID now, we can see we're all in root. Here's our command and control server on the Windows side. The Windows side is the client, so it's just a simple script to connect to the command and control server. So if we run this, we see we're connected, we can send a command. So we send something like ls. We get that malware executable we were talking about earlier. We send something like ps. We get all the processes running on the machine at the time. So over here, obviously, you don't see anything happening. But if we go back to the command and control server, we can still send through stuff like, and the user is unaware that these commands are being run. We can still do those same kill commands, gain root access, and the user is none the wiser. Nothing's changed in our console, and it's a very discrete hidden command and control server. To remove the rootkit from running, you would just remove it like any other kernel module. So you would do rmod, it's called malware_module.ko. And so once it's removed, you can start to see the CNC executable and the cnc.txt appear back, and we know our malware is done running. Defense against rootkits include ensuring processes act as expected. Hooked functions will act slightly differently. Keeping an eye on how these functions perform will be an indicator if they are hooked. You should also run both static and dynamic analysis on unknown software before executing it. You can look at it statically through programs such as Ghidra, and you can look at it dynamically by stepping through it on a virtual machine before executing it on your actual machine. For this rootkit specifically, one could monitor network communication, as it opens up a server and lets another machine connect to it and send data. Unknown network communication could indicate the presence of a rootkit. One broader lesson from the attack is to first prioritize prevention over detection. Rootkits purposely obfuscate their presence after being installed, so you should take necessary protections to prevent them from being installed in the first place. This can be said for virtually any malware. Another broader lesson from the attack is that rootkits work without your knowledge, meaning you should not assume any machine is safe just because nothing is noticeably wrong. You should be constantly monitoring your machine's activities and acting in such a manner that protects your data machine, even if you believe it to be uncompromised. This can include encrypting your files and making backups. This was my Linux kernel module rootkit presentation. Thank you for watching.